So hi there, how's it going? So today I wanted to demonstrate a very quick tutorial demonstration on running Gaussian. So Gaussian is essentially the gold standard of quantum mechanics and molecular modeling. So it's capable of performing energy minimizations, and it's capable of looking at vibrational energy and a whole host of things. So it's a very useful piece of software. If you don't know how to use Gaussian in computational chemistry, I think it's going to be a very useful tool for you to learn how to use. So the demonstration I just want to illustrate today is we're going to be looking at a cyclophane, and we're going to specifically look at a meta-cyclophane. If you remember the difference from your organic chemistry, ortho, meta, and para. If we have a benzene ring, if two things are connected ortho, they're on adjacent carbons on the aromatic ring. If they're connected, if the two substituents are connected with one carbon in between like this, that's called meta. And if they're connected opposite each other, that's called para. So I'm going to model a simple meta-cyclophane with and so this ring in the cyclophane, there's an aromatic part and then an aliphatic part. The aliphatic part, you can actually vary the ring size a little bit. And so this is a great demonstration if you're taking a molecular modeling class to look at the different energies of the different ring sizes, where you can vary n equals 1, 2, 3, up to 5 or 6 or whatever, and then see which is the most stable ring, which one actually works better. So cyclophanes are really useful compounds in organic chemistry. I'm going to start off in here. Let's just clear my screen. And so I'm going to start off by going into Mo. Now, we use the molecular operating environment by Chemical Computing Limited. It's a pretty good piece of software. It's a very good graphical user interface. And what's nice about it is it has an interface to Gaussian. So I'm going to go into my builder. I'm going to start off. Let's just call this molecule meta-cyclophane N3. I'm just going to do N equals 3. So that's my benzene ring to start. Nothing fancy. What I'm going to do is I'm going to make this a little bit easier for others to see. And then I'm going to take 1, 2, 3 carbons. And then I need to connect this carbon. And then I press down Shift. And then I can select both. If I hold the Shift key down in Mo, then I can select both of these two. I'm going to make a really long bond between them. Now that bond, yeah, that's not real, but it's connected, right? So all we have to do is apply energy minimization. And so the first rule of Gaussian is you always want to perform a simple molecular mechanics optimization prior to initiating the quantum mechanical engine of Gaussian. If you have really long bonds like this, you could get an error in Gaussian, and that wouldn't be good. So I've got this parameterized. I just do a simple energy minimization. We're going to do a gradient of 0.01, and we'll see that we've optimized this now. And we also kind of see the aromatic ring. Now, aromatic rings, that benzene should be planar. What's interesting here is the strain of these three, that the fused aliphatic ring is forcing this to not be perfectly planar in that meta arrangement. So we see that now if we do this in Gaussian, then we're going to get a little bit better. It'll be a little bit what we might see different angles a little bit, so we can compare that better. Now to run the minimization in Gaussian, I'm also going to go to Compute, Energy Minimize. We're going to do QM. Now Gaussian is a text-based software. And so whenever you're running in Gaussian, you're going to give it a text input file and it gives you text output, and then you use another piece of software like Mo or Avogadro to visualize the software. So I'm going to generate my Gaussian input file here in Mo. I need to tell it that I'm using Gaussian. This little wheel here, you shouldn't have to do this every time, but this right here tells me the path on my system to the G09 Gaussian direct executable. So that must be set in order to generate the Gaussian, right? So click OK. I'm going to do a simple Hartree-Fock optimization. I'm going to use the 631G basis set with polarizability as just a single star. I think that's sufficient for this demo. We do want to do a geometry optimization, so I want to check that. I want to keep my files, multi-step convergence. I want update connectivity because I do want this to update. And if I want to do vibrational energy, I could do vibrational frequencies as well. Then we could look at the vibrational frequencies in addition to that. That would be kind of cool. But we don't need to do that right now. Job title. So I need a title. I'm going to call it meta-cyclophane N3. I don't think I can put an equal sign in there. I like to try and, with these names, I like to try and avoid using complicated characters. That makes things easier. Now, if I just generate my input file like this, I'm going to run on one processor. And of course, you know, this atom, a little bit bigger. It might be nice to run this on more than one processor and run in parallel, because I do have, on this system, I have up to 8 to 12 processor cores. So I can run on additional processor cores in parallel. So that's kind of nice. In this case, I'm just going to I want to run on 6. In order to do that, I need some keywords, and I need the keywords nproc shared equals 6. Now, instead of running this here, I'm going to click on View QM Input File, and this lets me edit a text editor. And you'll see, first of all, it has my keyword for 6 processor cores. It has a checkpoint file. It has my HF, Hartree-Fock, and 601G star. OPT means we're doing a geometry optimization. And then this tells us about the molecule and the molecule name. And then these are the internal coordinates of the molecule, and this describes its connectivity. So in order to run this, I'm going to run at the command line. So I just need to type File, Save As, meta-cyclophane n3.com. This is my Gaussian input file. Hit OK. Now I'm done with that. I'm actually done with Mo. And I go back to my command prompt. And so you'll see I have meta-cyclophane right here. To execute Gaussian, I use the executable G09. And then the left arrow, this indicates that I need to put a input file into Gaussian 09. So that basically is code for my input file. I can also use a right arrow, and I can give it another name, such as meta-cyclophane N3G09. This is my output file, right? So if I run this, I'm just going to execute that. Now Gaussian is running. And what I can see in another window, I can type the top command to look at, to see if what's running. This L502.exe is the Gaussian executable that is executing. You'll see my percent CPU is 586.1. So since I'm running on 6 processor cores, it goes with 6%. Now it's not running anymore. Guess what? That means it's done, right? So I press Q to get out of the top window. I'm done with that. Now I can type ls, and you'll notice now I have a G09 file. This is a simple text file. I can edit this in gedit. And so this tells me all my input to start. And we can scroll to the end of the file. When all else fails, try the boss's suggestion. Those are words of wisdom from Gaussian. I like that Gaussian will always give you, when it finishes successfully, it always gives you a fun little quote. I kind of like those. So yeah, when all else fails, try the boss's suggestion. That's good advice. You'll also see the job CPU time. This executed in about 2.5 minutes. So that was pretty quick. And we always like to see, the last line says normal termination of Gaussian 09. So we have an optimized file, and so now we can, the energy. So let's see, if we kind of scroll through here, you'll see there's some of your Mulliken charges. And so what I'm going to do is just, this is a big text file, so I'm just going to do Control F, and I'm going to look for SCF. And whenever you see SCF done, this tells you the current energy. So this is the energy restricted Hartree-Fock is RHF, and so minus 3346.4 AU. That's called atomic units. We also call those Hartrees. Those can be converted to kcal per mole, and so then there is a conversion factor. I think if you actually go to Google, you can find that. Hartree units to kcal per mole. And you'll see that your conversion is 1 Hartree, or 1 atomic unit, is equal to 627.503. And so what you have to do is just do a little bit of dimensional analysis to convert the SCF energy to kcal per mole. Now the one thing, this SCF energy, you might want to do additional searches and find the last one that's mentioned, because the energy might be a little bit different, right? Every time it moves some atoms, it'll give you a different energy here, right? So you'll see. I think it's still, it didn't change much, but yeah. So look for the last SCF done line, and so that's an easy way to find, is just to do a search. Control F. To do a search for SCF, and then Control G will do the same search over and over again. So that's kind of nice. Now you can also load this G09 file in Avogadro to view the actual converged output, because Mo will not actually read that. So here's my G09 file. I open this. And here is my converged meta-cyclophane. Now one thing with this, you'll see we're still planar in this ring, but they didn't quite label all of the bonds. So it looks like they're all single bonds. So be a little bit careful with some of the bond labeling in there. But you also see, very similar to our molecular mechanics, this aromatic ring down here is not perfectly planar because it's being constrained by the cyclophane ring. So that is how we run a Gaussian calculation using more than one processor, and that's how we visualize our output. So I hope you find this video useful, and yeah, you can also go ahead and click like on the YouTube, and if you find that useful, we'd appreciate that. You can subscribe to my channel as well, and thanks.